start recording now.
So you see my screen?
Yes. And I'll also point to you like like 1 minute left whenever you have a minute, okay?
When? Maybe after 6 minutes.
Yeah, like around 5 minutes, I'll tell you.
Oh, okay, yeah, sure.
And then we open for questions.
Just a minute. What am I doing? Yes, it's, yeah. Oh. So, Raphael, you are muted. I don't know if it's maybe...
Yes, I'm muted just for now. And then whenever there's a question, I'll unmute.
Oh, okay, sure.
All right, it's a pleasure to have Ido here. He's giving the first talk on can a natural number be negative? A problem connecting proof complexity and some very outstanding conjectures in algebraic complexity number theory. Okay, thanks, Ido.
Thank you, Raphael. Can you hear me? Right.
Yes.
So thank you for coming for the first talk of the first session of the first online STOC. I am Ido Tzameret. This is a joint work with Yaroslav Alexiev, Dima Grigoriev, and Eduard Hirsch. And the title is, Can a natural number be negative? The actual formal title is, as the paper shows, this is the subtitle. And this question, this absurdly sounding question, we want to make it precise and connected, as Raphael said, to algebraic and circuit complexity. So let's see what we have done. And this is what we start with. So we introduced the binary value principle, which is a simple linear equation like this. So we have the xi's as n bits, and we write this linear equation, and the left hand side is just the value of a binary number written with n bits, right? The xi's are 0, 1, and the right hand side says that the value is actually negative. It is -1 in this case. So this is obviously when the xi's are 0, 1, this is unsatisfiable, right? So we want to think, and we call this the binary value principle, and we want to think of how to actually prove that this is unsatisfiable, to refute it in certain proof systems. And what we do is the following. We connect it to algebraic and semi-algebraic proofs, and in some sense to algebraic complexity based on, as Raphael said, and a very interesting and elegant assumption from in the hardness of algebraic circuits. So I'm going to go very fast and show you just the 3 main results that we have. And what we have is the following. So you don't really need to know all the proof systems because this is proof complexity. We have a very nice web of proofs, and I grade them out here because you don't need to know them. You just need to know that we work here with IPS, the ideal proof system as introduced by Grocher and Pitassi. And IPS is ideal proof system is a pun, but the point is that it is based on reasoning over the ideal of polynomials. So this is why it is IPS. It is a very strong proof system that is important for us, and it is algebraic. So this is here, and let's see what it is. It's quite easy to actually explain it. So if I want to refute a set of equations, or polynomial equations like this, the fi's are all equal 0, I want to refute this. I say it is unsatisfiable and I want to prove it. What do I do in IPS? I just write this simple sum, this polynomial combination of the axioms, fi's, and I say this simple sum is equal as a polynomial identity to 1. And this is IPS. Basically, this is, for those who know Nullstellensatz, the point in IPS is that these GIs are written as circuits. So that is because this is why it becomes very strong, because instead of counting the number of monomials or degree, we write this as circuit, and And that is the point. I'm slightly simplifying things. And this is where we are. Now, what we are going, and what we showed is the following. This is the first result. The first result is that a conditional lower bound on IPS. So again, this is very strong proof system. It simulates a lot of proof systems in proof complexity like extended Frege. But in proof complexity, we don't know much. We don't know almost anything about lower bounds for strong proof system. And this is even bigger than strong. This is very strong. It is not even polynomially verifiable. So we succeeded to do this with paying something. So we show this lower bound on IPS, but we paid in the fact that we have some condition. This is also not known in proof complexity. Conditional lower bounds are not known. So we have this condition. The condition is the Shub and Smale hypothesis, which says the following. There is no small, namely polylogarithmic circuit size of computing factorials like this. So if I want to compute from 0, 1, and -1 m factorial, I cannot do it with steps which are polylogarithmic in m. And this is the assumption, and we get the lower bound on IPS, refuting of this instance, precisely the binary value principle. So the binary value principle is hard for IPS based on this assumption. Of course, we paid with the condition. Another thing is that this is not a CNF. So this is not a Boolean tautology, and so we cannot apply it to the logical setting of Frege and extended Frege. But still, it is quite interesting. Now, the second result that we show is the following. We show that we want to say something about semi-algebraic proofs. So we want to show that semi-algebraic proofs are actually separated from the algebraic proof system. And what we showed is we introduced for this reason a very strong proof system, which basically simulates all known concrete proof systems that we know of. And we call it the cone proof system, like IPS. It works over the cone. And what it means is just that I have a SOS written as an algebraic circuit, very similar to IPS. You just write it like this. You take the assumptions and you say they are bigger or equal than 0, and you want to refute this. Yeah, I'm finishing in 1 minute. You want to refute this one, and what you do is you take the products, and then these products you product with SOS, sum of squares, any squares of a sum of squares of polynomial, and you say this equal as a polynomial equality -1. If you have this and you write this SOS as algebraic circuits, this is CPS. Again, I'm slightly simplifying, and what we show is that binary value principle is very easy for this CPS, and actually we get slightly stronger result. All proof system of semi-algebraic, all semi-algebraic proof system, even SOS, is uncomparable to IPS, because IPS, the stronger algebraic proof system, cannot prove binary value principle, but SOS does. And this is the final slide. The third result is that not only a binary value principle is hard for algebraic proofs, it is also complete for semi-algebraic proofs in the following. So I put this slogan: IPS plus the axiom schema of the binary value principle simulate CPS, namely the cone proof system. So basically this is in some sense complete. Again, I'm slightly simplifying, so I encourage you to look at the final paper. And I think these are quite elegant results, very interesting, and I hope
okay.
My talk.
Thank you very much, Ido. We have one question from the audience. So does HARP for IPS mean that the proof length is exponential, or you can only prove super polynomial but not exponential?
Right, it is a super polynomial, right? It is super polynomial, I think. Yes, it is a super polynomial.
Okay.
But I will, yes.
Okay, and another question is,
what is the motivation?
Oh, you can see
the
now.
Binary value principle specifically. The motivation, as I said, first, it works. So it actually is giving you the lower bound. But if you want more, then it's actually not only that it's hard, it's actually can be said to be complete for semi-algebraic. Namely, it's not just very artificial, it's a very simple linear equation. And if you can prove it, then then you can simulate semi-algebraic proofs. It is also motivated by work of Beam and all. It is related to algebraic and Boolean reasoning, but basically, I would say it works, and it is also complete for semi-algebraic proofs.
Okay, any more questions?
Okay. No open questions.
Okay, so what are your, do you have what are your dream open question, Ido?
Yes, of course. So the most will be most impressive is the following. As I said, we proved this lower bound here on the IPS. But the point is, we prove it for the binary value principle, which is not, it is not a CNF. It is not a propositional tautology. So basically, we didn't get a lower bound on extended Frege, neither even conditional.
So the dream would be to have something that is like defined as a constraint satisfaction, right? To connect extended Frege.
Yes, I think it's not completely ruled out because it is conditional. So maybe we can have some condition and get some strong extended Frege or Frege lower bounds. I certainly think that even Frege lower bounds are maybe capable of achieving via this algebraic paradigm. Okay. I think this is the dream goal.
Okay, thank you very much. We're going to switch speakers now. Thank you, Ido. Ian, can you start setting up?
Oh, should I do something?
Yes, can you, yeah, very good.
Stop sharing.
Yep.
All right. Can everyone see that? And can everyone hear me?
Yes.
I think so.
All right, let's get started. All right, thanks for coming to the second talk of the first session of the first virtual STOC of the whatever. I'm going to be talking about automating the cutting planes proof system. This is joint work with Sajin Karath, Mika Goose, and Tony Patassi. So in proof complexity, we define a proof system as being a way of deriving a contradiction from an unsatisfiable formula tau. So the proof system is the rules of the deduction, and automatability is the algorithmic question. It asks, can we actually find a refutation of a given unsatisfiable tau efficiently? Where efficiently for us will be defined as polynomial in the size of the shortest refutation of tau in the proof system. And this is instead of polynomial in the input length, simply because for most proof systems, we actually have examples that require huge refutations. So there's a whole line of results showing that it's hard under some assumption to automate various proof systems. Early on, we knew that the harder systems like Frege were hard to automate under crypto assumptions. But up until 2018, the landscape for weaker proof systems was pretty spotty. We knew some systems under ETH or various other assumptions like fixed parameter tractability assumptions. And for other systems like cutting planes and SOS, we didn't know anything. So this changed in 2019 with a really amazing result from Itserius and Mueller, which showed that resolution is actually NP hard to automate, resolution being one of our most fundamental proof systems. And since then, there's been a huge flurry of work showing various other systems are NP hard to automate, including cutting planes, which is going to be our talk today. So cutting planes is a refutation system defined in the late 80s. The setup is you have a set of linear inequalities such that there's no integer valued points that satisfy all of them. And to certify this fact, we're allowed the following deductions. Given any two linear inequalities, we can derive a new one as long as all integer valued points satisfying the original two lines satisfies the new one as well. And from here, we're going to work our way to a contradictory line, namely something like 0 greater than or equal to 1, which will certify the originals were unsatisfiable over the integer valued points. So to talk about our non-automatability result, I'm going to talk about the Itserius and Mueller one for resolution. Their key lemma was a reduction from 3-sat to unsat, such that the unsatisfiable CNF tau had resolution refutations. The smallest resolution refutations depended on whether the original 3-sat instance was satisfiable or not. And this gives you a non-automatability result, because if you assume you had some automating algorithm, and you run it on this formula from the reduction, it will only halt in polynomial time if the original 3-sat instance was satisfiable. And so because of this, you can distinguish sat from unsat. So then our main result, showing that it's NP hard to automate cutting planes, is via a very similar reduction from 3-sat to an unsatisfiable system of linear inequalities. And instead of working from 3-sat, we're actually going to work directly from Itzerius and Mueller's unsatisfiable tau. And this is a process called lifting. So in lifting, the idea is we're going to take each of the original variables in the formula tau and replace them by an inner function, which we call the gadget, on a fresh set of variables. And the gadget's going to be chosen such that the best cutting planes refutations of the composed formula look something like the best resolution refutations of the original formula. And so here is a theorem that precedes us by a couple of years that actually shows this. There's a lift such that the size in cutting planes is n to the width in resolution, where width is the maximum number of variables occurring in any line in the best resolution proof. And if you compose this with Itzerius and Mueller's reduction, what you get is that the size of the new system A in cutting planes is like n to the width in their respective cases, the resolution width. The problem is resolution width is linear in both cases. So you actually get an exponential upper bound, which doesn't really give you anything. But what they showed was that a related notion of width, called block width, has exactly this separation we want, constant in the good case, polynomial in the bad. And so what we prove is a new lifting theorem, which lifts block width in resolution to cutting plane size. And from here, you actually get the separation that you want. Okay, well, I've got 15 seconds, but let's just call it there.
Okay, thank you very much. Yeah, for the nice talk. And I believe there is one raised hand in the audience. Let me allow that person to talk. Okay, LMM, can you ask? Do you have a question? Okay, I'm gonna, okay, so then let me, Shahar, can you ask your question now?
Can you hear me? Oh,
yeah.
Can you maybe define block width?
Say it again.
Can you define? You said block width.
Oh, sure. Yeah. So I mentioned before that width is like the maximum number of variables occurring in any line. I didn't define resolution, but all the lines are clauses. So the width is the maximum number of variables occurring in any clause. And then block width is only defined with respect to a blocking up of the variables. So you have to define some chunking. But from there, block width is the maximum number of blocks touched by any line in the resolution proof. So you can define your blocks such that block width is trivial, like every variable is its own block, or there's one block with all the variables. But the goal is to basically choose them in a way such that you can separate good instances from bad instances. And in Itzerius and Mueller's case, this is a really natural blocking up. And we basically just lift straight from theirs. So.
Thank you.
Anyone else?
Any more questions?
May I ask something?
Yeah.
Sure.
Yeah. What is the? Can you just capture in one sentence what is the new thing over the Itzerius and Mueller result? The gadgets, or is it completely different structure?
There wasn't a gadget in Itzerius and Mueller per se. They defined a tautology, which actually gave this gap. Ours is more in ours is a lifting theorem. So originally these actually come from communication complexity. So our new thing isn't so much an innovation in terms of what satisfiable and unsatisfiable, or you know, the size of some specific formula, but rather it's in transferring resolution lower bounds and upper bounds into cutting planes lower bounds and upper bounds via this gadget, which the gadget is the standard index gadget from communication complexity. So we're doing a very different thing than Itzerius and Mueller, even though we're using theirs as a springboard.
Okay, thank you.
Yeah, there's one more question. So Massimo is asking, usually in lifting, you apply one function for each variable. How do you lift sets of variables in a block?
Right. So usually to lift to a block, we do multi-party communication complexity, which is to say we assign each of the variables output that we want to output in a block to a different player, to a different Bob, and what the goal of this is to make it so that computing each of the variables individually is just as hard as computing all of them together. And yeah, I guess that's the intuition, roughly speaking.
Thank you. Do you also, there's another question by Christopher Jones. So in terms of proving NP hardness of automating SOS by size, do you think a variation on this argument will work, or do you need new ideas?
So this is probably a better question for the other big paper that came after it, Series and Mueller, which was for Shirali-Adams and for polynomial calculus. So yeah, for SOS size, they also prove, if I recall correctly, I don't know if you'd call it a lifting theorem, but a reduction. You should probably talk to them because the Shirali-Adams is much closer to SOS in terms of the measure of size and the arguments used. I don't think that there's a direct connection to something like communication complexity, so I don't know how you use our gadget lifting, but you can check how they do Shirali-Adams, and maybe there's some way to prove positive semi-definiteness of their reduction.
Thank you very much, Ian. I guess we'll switch to Dmitry Sokolov. Can you start setting up, Dmitry?
Yeah. Do you hear me?
Yes.
Oh, great.
Just to all the participants, so we have, it's 40 minutes for the talks, but later, I mean, there's a break of 20 minutes and it won't be live streamed. And you know, if you want to, you can ask questions. I guess the speakers will be around still. So, all right, Dimitri, whenever you're ready. So
yes, I'm ready.
Okay.
Let's start. Hello, everybody. I'm going to present my paper about semi-algebraic proofs of plus and minus one variables. Well, it's again about proof complexity, and to be more specific, it's about semi-algebraic proof complexity. So we have some system of polynomial equalities and polynomial inequalities. And we usually pay attention only to some x's from 0, 1, or for plus and minus 1 values. How we can certify that this system is unsatisfiable? So there is no either Boolean solutions or plus and minus 1 solutions. One of the most famous proof systems is sum of squares. If you have this system f and h, so we can write this sum. And if the sum equals to -1, that means that there is no common solution for this system, because if you have a solution, it will evaluate first part to 0, second part to 0, and the last part it will evaluate to some positive number. So if there is some solution, it's impossible to create the sum. And for each system, we can write the sum such that it will be -1. Another proof system that we consider is polynomial calculus, but it's a proof system that deal only with system of equalities. And we can derive our proof step by step. We can start with equalities from our system. We can multiply it by variables, and we can consider linear combinations. And in the end, we want to derive trivial and satisfiable polynomial, just one. Simple example, if you have this system, we can write this proof. So we start from our equality multiplied by variable, and we consider some number of linear combinations, and we can use also our axioms that says that we care about plus and minus one solution in this case. Well, we have a lot of different proof systems, and for some of them we can prove lower bounds, and for some of them we cannot. But why we pay so much attention to proof complexity? In my opinion, it's interesting that if we consider very weak proof systems, it's enough to prove lower bounds for them to prove lower bounds for monotone computations, either monotone circuits or monotone span programs or other models. If we will prove lower bounds for strong enough proof system, it will give us lower bound for circuits. So in proof complexity, we have some natural intermediate steps like Frege systems, sum of squares, and other proof systems. And we have two general frameworks how we can prove lower bounds for proof complexity. For proof systems, it's restriction technique and monotone interpolation. Unfortunately, all of these techniques will not give us anything if we deal with plus and minus one variables. And there is an important reason for that, because in all these proof systems, we can simulate, we have efficient representation of mod P gates. I mean, if we write our polynomials in terms of plus and minus one variables, we can represent parity as just a single monomial. That is totally not true if we deal with 0 and 1 variables. And it's important because we cannot prove anything for proof system that have efficient simulation of mod P gates. Here we have some results of this paper. So we actually can prove something. We have lower bound for sum of squares over plus minus one variables. We start with any system that is hard in terms of degree, leave it as it was in previous paper, but with very simple gadget. It's just majority of 3 new variables. And after that, we have lower bound in terms of size. The same holds for random CNF formulas, and it holds also for sum of squares and for polynomial calculus proof systems. And the last result is more about separation. We can also prove lower bound for pigeonhole principle. Surprisingly, technique is generalizable to more complicated proof systems where we can allow any encoding of variables. I called it shifted sum of squares and shifted polynomial calculus. That means that we can use any encoding for the variables, not either 0, 1 and plus minus 1, but any other values. And some open problems that may be interesting. In my opinion, the first open problem, it seems to be specific, but it's general because it requires some new technique for proving lower bounds. Thank you for your attention.
Thank you very much, Dimitri. Questions? Dimitri, maybe do you want to keep the slides there for now, just for people to ask questions, just in case they, no worries.
Sorry. Yes.
In the meantime, I guess I'll ask a question. So can you show, oh, okay, no. By the time that I decided, 2 people ask questions. Okay, so there's a first question is, hi, what does it mean that in the shifted SOS, you can do any encoding?
Like you can choose any 2 values, A and B, from your field, and you can use any represent. Suppose you have some system in terms of axes. And axes are Boolean variables. For example, you can consider linear system modulo 2. But now, if you switch to plus and minus one variables, you have efficient certificate of unsatisfiability now, because you have efficient representation of mod 2, of parity gates. And shifted means that you can use like any encoding that you want. You can deal with Boolean variables and with plus and minus one simultaneously. So you have like extension variables for each Boolean variable that you have in the beginning. Does it make sense?
Okay, thank you. The next question is from Russell. Russell, I don't understand your question. Can you ask?
Can you also use this technique to prove lower bound for variables that have more than 2 values?
Oh, yeah, it's easier to prove lower bounds for variables that have more than 2 values, but unfortunately, this technique is too powerful in some sense, and it requires a lot of properties from your system. So if you have a very good system that satisfies a lot of properties, then you can apply this technique for other settings, yes.
Thank you. So Paul is asking a question. So do we have separations between polynomial calculus mod 3 and mod 5 using plus or minus one variables, say?
Using plus and minus one variables, it's not really clear, but if you consider shifted versions, then if we deal with real numbers, then we can solve all mod P setting formulas in particular. So these systems are separated from classical systems, yes. Okay. So yeah, actually, if you have proper encoding, then we can solve mod P setting formulas.
Thank you very much. Okay, maybe we should switch to the other Dimitri.
Okay, I'm ready.
Okay, whenever you are. So we're happy to have Dimitri talking about QCSP monsters and the demise of the chain conjecture.
Thank you for the introduction. Thank you for coming. This is a joint work with Barnaby Martin. And today I will tell you about QCSP monsters and the demise of the chain conjecture. And I will start with the definition. What is QCSP? This is quantified constraint satisfaction problem. So assume that we have a finite set A, and on this set we have a set of predicates or relations gamma, and we call this gamma a constraint language. Then for every gamma we consider decision problem QCSP over gamma, given a sentence where we use both quantifiers, we use predicates from gamma, and we use only one connectivity conjunction, and we need to decide whether this sentence holds. For example, if we are on three-element domain and we have just one predicate inequality in our constant language, then we may consider this QCSP instance, which is true, or this QCSP instance, which is false, and so on. And the main question we are addressing today is what is the complexity of QCSP for different constant languages gamma? And first, I want you to look at a bigger picture. So if we consider quantified constraint satisfaction problem, we use both quantifiers and just one connectivity. Or we may consider dual problem where we have a disjunction instead of conjunction. And here we don't have classification, and we don't know what complexity classes can be achieved like this. But if you consider other variants of first order logic formulas, for example, if you consider existential quantifier and disjunction, here everything is trivial. If you consider existential quantifier and conjunction, then this variant is just CSP, constraint satisfaction problem. And here we know that the complexity classes we can achieve are just P and NP complete. And it turned out that for any variant, we have classification. And we know that the only complexity classes we can achieve are very simple. It's either P or NP complete, or co-NP complete, or P space complete. And so in the whole picture, in the whole table, the only open question is the complexity of the quantified constraint satisfaction problem. This is our motivation, why this is really important. Okay, and for QCSP, we actually don't know a lot but we know something. For example, we know that on two-element domain, QCSP over gamma is either in P or P space complete. Here, some other partial results are listed. But anyway, about 2 years ago, everything was really great because 2 years ago we had an amazing conjecture by Chen, and this conjecture described the complexity of QCSP over gamma for for all constant languages gamma. So now Chen conjecture. He conjectured that QCSP over gamma is in P if gamma has two properties, PGP and weaknu. Today I don't have time to define these properties, but these are just two simple properties. Then QCSP over gamma is NP complete if gamma has PGP property, so the first one, but it doesn't have the second one, doesn't have weaknu. And it's P space complete otherwise if gamma doesn't have PGP property. So it was an amazing conjecture describing everything. We have just 3 complexity classes and we had an easy classification. And the only problem is that it turned out that it doesn't hold. About 2 years ago, we found a constant language on 3-element domain, giving the complexity class QNP. So QCSP over gamma is QNP complete. And this was really terrible because we planned to prove this conjecture and to get a classification. And now we get this QNP complete class and we didn't know what to do. But then everything went even worse because we found constant language on 4-element domain such that QCSP over gamma is DP complete. And then finally we found the constant language on 10-element domain such that QCSP over gamma is theta 2P complete. And for example, at that time, I even did not know this complexity class. So before we expected to get beautiful classification with just 3 complexity classes, now we have 6 of them. And we still don't know whether there are some other monsters, whether there are some other complexity classes that can be expressed as QCSP over gamma. And these are our negative results, and now positive results. We managed to prove Chen conjecture for all constant languages gamma containing all unary relations. This case is called conservative case. And the main result of our talk, we found classification for 3-element domain if we assume that our constant language contains all constant relations, which is very natural. We assume that we can use constants in our sentences. And it turned out that in this case, QCSP over gamma is either in P or NP complete or QNP complete or P space complete. So it's like this. But the main question remains open. We still don't know anything. We don't know what are there any complexity classes except for P and P complete, QNP complete, P space complete, DP complete, theta 2P complete. And we don't have any conjecture on how it looks like. That's everything. Thank you.
Thank you very much, Dmitry. We're going to open up for questions now. Okay, Shaharia, you can ask a question.
Can you go to the previous slide?
Yeah.
Yes. So you wrote your result for 3 elements when you contain all of the unary relations, but if you have 4 elements or 5 elements, is the same result, or you don't know what's going on?
I don't know. And we already know that on 4-element, we should get this new complexity class DP. And so this class should appear in classification. And yeah, we don't know how it looks like.
Okay, thank you.
So like the main reason we obtain this result is because 3-element domain is small enough to describe everything. And already on 4-element domain, we know nothing.
Okay, thanks.
Okay, any more questions? So I have one in the meantime. So in the YouTube talk, you're saying that you could modify PGP and EGP constraints so that like you could try to get a more general version of the chain conjecture to be true. What would be like candidates for these modifications?
Actually, now we don't have a good candidate, and like now we have 6 different complexity classes, and we don't have a hope to describe everything. but we have a hope to describe all tractable cases. And we believe that we need to modify this PGP definition somehow, but actually we don't have a good candidate. We have only some ideas.
Okay, thank you. Okay, there is one more question. So Rick is asking, do we know anything in the case of languages on 3-element domains where those constant equality constraints of the form x equals to a aren't all present?
That's a good question. That's another problem. We actually don't know a lot for the case when we don't have this constant relations. And the problem is that now we reduce QCSP to CSP. If we have constants, we can reduce QCSP to CSP. And if we don't have constants, then we don't have this reduction. And that's why for this case, we really know nothing.
Okay, thank you. Okay, so I think that's, if there are no more questions, that's the end of the session. Thanks everyone for coming. Thanks all the speakers for the very nice presentations. I'm gonna clap for everybody. Yeah, thank you very much. And if you wanna hang out here a little bit, we'll stop the recording now. And yeah, if other people want to ask questions, please just raise your hands. I can unmute you and